Alright, this video is going to be on section 11.3 in our pre-calculus units. It's on the value of E, and it's the number E, not the value of the letter E. And I like these kind of visuals here. The first is just has a lot of words that has to do with what E is, and it really kind of talks about a lot of different areas you use it in, and it has a lot of interesting words in it. The next one has to do with where we see E and how E is shown in nature, and it actually shows here how E is shown in actually a lot of different shells that are shown and are around in nature. Alright, so today by the end of this class or this video, we're hoping that you're really kind of more familiar in how to use this exponential function of E. And so number E can be rounded to about 2.71828 and actually goes on and on forever, a lot like pi. It's an irrational number. It was discovered when people were trying to compound money, and at first you thought, well, I compound interest every year, which means you take in a percentage of the money and you add it onto what you have. And they realized that, hey, how often could you compound it? Could you compound the interest 4 times a year? Could you do it every month? Could you do it every day? And they realized that you could kind of keep compounding it regularly, and they found this value E that meant if you compound it even more than every, like daily, but even a little bit less than daily, it has to do with the fact that there's 364.25 days in every year, that they got this value at the same time, no matter how much money they were talking about or what the percentage rate, that it always came down to this value E. And so it actually has become a part of a lot of formulas that have to do with finances. So this is kind of more information. This is from Wolfram Alpha. It's actually called Euler's number, and I know this word here, Euler, it looks like Euler, like Bueller, but it's not. It's Euler is how it's pronounced. And it has a lot to do with natural logarithms, and we're going to get into logarithms in the next section, and then natural logs a couple sections after that. But it's in a lot of different areas, and it's really a good topic to do some more independent exploration. Even this is kind of fun. You can take a minute and you can read this. You can pause the video and read all the top 10 reasons why E is better than pi, but it certainly does not get the same notoriety, let's say, as pi does. So let's talk about, though, where is this E used? And it's used a lot in growth, decay, and compound interest. We're first going to talk about growth and decay. When they're going to use E, and when you know how to use E, they'll usually give you your own equation, or they're going to be talking about this K, which is a constant. So in other words, when the rate is given as a K and not as a rate, that's when you know, hey, I'm probably going to use this equation that has E. Where we have our start, our initial value, our start value, all right. E is just our constant number. I want to show you how to find that on your calculator, any calculator. K is a constant. All right. And T is your time. Now, time can vary. It can be weeks. It can be months. It could be years. It really depends on the context of the problem you've been given. Let's talk a little bit more about this the constant K. When that constant is positive, that's indicating that we have growth, because the number was going to get bigger. When that constant is negative, that's when we have decay, because the number is going to get actually smaller. So we have growth and decay. Now a second formula that we're going to be using is called when we have continuously compounding interest. And it's also often called PERT, and hopefully you can kind of see where the P, E, R, and T comes from, where we have our start, and here we're talking about money, so it's always starting money. E is just the number E, that 2.71. R is our rate, and that is usually you're going to have to put it into a decimal, so it's going to be a percent that you have to put yourself into a decimal, and T is time in years. Always, this one's always in years. There is no how many times is it compounded like we had in the last chapter. This one is compounded continuously, so over and over it's going to get compounded. So let's first look at a problem. This is a problem out of your book, and the book had some good information about this chemical called DDT. DDT is a chemical that was used in the past. I think it's been outlawed now. They use it to get rid of bugs and help their crops to grow stronger. But they found out it was harmful in the air. And so now they've realized that DDT does degrade into harmless materials over time. So in 1973, they started with this 1 times 10⁹ kilograms of DDT in the environment. And then for this DDT, K equals negative 0.0211. And notice how K is negative, so it does decay. So first they say, okay, write the function to model the amount of DDT remaining in the environment. So we're going to call this as the amount remaining. And we're going to start at this 1.0 times 10 to the 9th kilograms. And then to the power of times E, all right, because it was the starting number times E. And then you have your K value, 0.00211. So 0.0211, sorry, I think I said that wrong. And then multiplied by the time. And we don't know the time in our equation here. So we're saying times our time. It should be noted our time is years for this one. So then they say, okay, use that formula. And here I'm going to write just 10 to the 9th. 1 times 10 to the 9th is just 10 to the 9th. And then this would be, we're talking about in 2005, then we'd have to go off to the side and say, hey, how many years is that? We'd take 2005 minus 1973, we get 2, and what did I get? I got 32 years here. So it's e to the negative 0.0211, and then I'm going to multiply it by 32 years. All right, so we need to put that equation into our calculator, and that's what I need to talk about, is how do we put that equation into our calculator. So 1 second, please. All right, so get to the calculator here, and first the value we had was 10 to the 9th, so I'm going to put in 10 to the 9th, 10 to the 9th power right here. And then we're going to multiply it by E. E is found under second ln, second natural log, and a lot of times that's where it is. Oh, I made a mistake. I apologize. I'm going to have to delete this. I wasn't out of my exponent. So this particular, I'll just clear it out. This particular calculator, when you get into an exponent, you have to hit the arrow key to say, I'm out of that exponent now, and I didn't do that. Sorry about that. Oh, I'm just having a day here. Okay, now we're going to go multiplied here by our E, second natural log is our E, and automatically E always has an exponent to it. It's only used when we have an exponent, and so it always kind of prompts us to say, what is your exponent? I'm going to put a parenthesis around here, and I'm going to say a negative 0.0211, and it was times 32 for the days. I'm going to put parentheses. Now, I didn't have to do the parentheses. In my calculator here, I could have done 2 separate parentheses, and it would have stayed up there in the exponent. Not all calculators do that, so you're going to see me having these parentheses a lot because depending on your calculator, it's really important to get these parentheses right. So for an answer here, I got 50905459. I'm going to call it about 5.1 to the 8th power. So since I was given a number here, I'm going to say it was about 5.1 times 10 to the 8th power. All right, so I kind of rounded my answer there. I could write it all out if I wanted to. It's kind of a long answer to memorize. All right, so now we're going to say, okay, now we have 25 years. We're going to invest this $10,000. And this investment is earning us 6.75% interest, compounded continuously. And then compare it if it was semi-annually. So we're going to start here with, so what we know is we have our formula, that the amount of money you have is the principal times our E to the rate times the time. This is when it's compounded continuously. Well, our principal here is our initial money that we add in, our $10,000. We have our E. Our rate has to be in our decimal, and this is probably one of the most common mistakes I see is people forget to put that in a decimal. And then our years is 25. When we multiply that out, we get $54,059. Okay? Now it also says, hey, same problem, but what do you get if you instead had it compounded semi-annually? Now, the formula for semi-annual was where you took the principal, and then you took 1 plus the rate over the number of times in a year that it was compounded, and the number of times times the time. All right, so I need to get that out of the area. Sorry. So in this case, it would be the 10,000 times 1 plus 0.0675. Compounded semi-annually would be that it was 0.065. which turns out to be 52574. 52,000. So really you only gain $2,000 from having that compounded continuously versus compounded biannually or each semi-annually, twice a year. But I'll tell you, with $10,000, okay, it's $2,000, which is still significant. What if it was, you know, $100,000? It was a house mortgage, which was $500,000. Then we're talking a lot of money there. And so it's really definitely something that is helpful when something is compounded continuously. So your assignment that I want you to work through is here. And I'm going to kind of go through slowly, show you all the different problems. But I want to work through a couple of the problems with you. Here's some of the other problems. I really like 11. I think it's a good problem, as well as 12 and 13. So I want to go through 6 and 7 with you. So we're going to start with Bakersfield. So the first question is, we have this equation. Y equals 33,430. And this is kind of like an equation that Bakersfield came up with. Whoops, 7. And then to the t. So that's our equation. Because our k, and our k is shown right here, is positive, we know that we're dealing with growth. Remember how this is our starting value right here as well? This is our starting value. Well, that starting value is where it would be when this particular value starts. So in 1950, so it says what is the starting or the population in 1950? Well, that was our starting value. Here, all we had to do is for C is instead of this t here, we would have added in our time, and our time was 60 years. Okay, and then we just had to calculate it out. We had to take 33,430 and multiply it times e to the 0.0397. So that turned out to be 361,931. Okay? So now we're going to look at problem 7. Now the Kwans are saving for college, for their daughter's college. Their daughter's in 1st grade, and so they know they're going to save for 12 years. And right now they have $12,000, and they're going to invest it at a rate of 6.4%, which is a pretty good rate. And they're going to say, okay, how much are we going to have when our daughter gets to college? So we're going to use that principal and then the e to the rt equation. Our principal here is 12,000. The rate was 6.4, so 0.064, and then the time was 12 years. All right. So let's work that through here. I'm going to get the calculator up. We had here our 12,000, and we multiplied it by our e, and then we took that to the power of, it was 6.4%, so 0.064, times 12 years. We get 25,865, and I'm going to round it to that. So it was 25,865. 25,865. Right now at the University of Minnesota, they're estimating that their first year of college for next year's freshmen is right around $28,000, and that's not including books and some other incidentals. So while they did a really good job of saving, that $25,000 is barely going to get through 1 year, which is kind of scary, but that's kind of how it is. So hopefully you got a good idea of how we use compounding continuous formula and when we have growth and decay. I do want you to do this assignment on page 714. There's some really good word problems in there. Good luck.